Yeah. We can also arrive at expression for motional EMF in another way. So let us derive the expression for EMF in another way. Already we got an equation for the EMF, that is E is equal to B LB. Yes. Now see. So here this is a rod, that is a P, which will move across this rod with the speed, that is a V. Now, for a time being, let's take one charge. Let's take a one charge. One charge Q is there. And now you are moving the rod PQ along this direction with the velocity V. And that charge is included within that rod PQ. So that is why whatever the velocity with the velocity PQ rod is moving, the same velocity that particle will have. Because we know about the translatory motion. Okay, it is a kind of the phenomenon here is a translation motion where all the particles have the same velocity of the whole body. So that is why the charge particle which moves with the velocity v, since it is enclosed within this rod, that is a rod P. So that's why this charge Q also has the velocity v is the same as that of the rod Q and it will move along this direction. So if I consider that one charge, it will have a number of charges, but for this situation I am considering only one charge. And it looks like a charge is moving in the presence of an external magnetic field. If you look at the situation, actually we are moving the rod PQ, it has a charge. So now the charge is moving with the velocity, so which looks like a charge is moving in the presence of any external field. Then what happens if a charge is moving in an external field? Then there will be a force acted upon the charge particle due to this magnetic field, and that can be calculated. Let us calculate the force acting on that charge. Force acting on Q due to magnetic field. Due to magnetic field. Let's add the force. Force is equal to F is equal to, what is the formula? That is Q into V cross V. That was a formula for a force acting on a charged particle moving in the presence of any magnetic field. Now see. So see, this is the direction of velocity of the charged particle, and if I curl my finger like this is the right hand rule. I am applying the right hand rule here, and this is my right hand, and all my fingers are pointed in the direction of velocity of the charged particle. I am curling like this, so which indicates the direction of the magnetic field. Now see, this is the direction of magnetic field. You are crossing your fingers, that is why it is a cross product. F is equal to Q into V cross V. So the angle between this magnetic field and velocity is 90 degrees. See, this is the direction of velocity, this is the direction of magnetic field. So the force acting on this charge particle is downwards, which is towards Q. So field force acting on Q due to magnetic field is towards Q. Hope you understood. Towards Q. So F is equal to Q into V. Theta is a 90 degree there, Q into V cross V, Vp sin theta, theta is a 90, that's why we get F is equal to Q into V. Now we got the force. So there is a force acting on this charged particle due to this magnetic field, so which is along this direction. That is why this charge will move from the side P to Q, because there is a force due to that magnetic field. So then, what is the work done by this magnetic field on this charge? There is a force on this particle, charged particle, because of this magnetic field. That is why this magnetic field will do some work. So let's find the work done. Work done by magnetic field on Q is W is equal to, how to find the W? W is equal to force into displacement. Force into displacement, that is F into B. Okay. So before that, here we have written X is this side and L is this side. So X is that side, X is L is the length of S. So force into length, what is the distance that the charge will move? That is L. From P to Q, that's why the length is L. F into L. So we know the formula for F, that is Q into B into B into L. Q into B into L. Now we got the equation for work done. So if there is a work done to move a charge from one point to another, that will store as energy. That can be called as a potential energy. So here we can say that it is a potential. So if the circuit is open, then we can say the potential developed across the terminal is called as an EMF. So that what we can calculate is, we can write the value of EMF, or you can say potential. Potential is developed because of this work. Then potential developed is, how to write the potential. So equation for potential, we have already used this equation while discussing the second chapter. There we have written potential energy is equal to, W is equal to, work done is equal to V into Q. This was the equation we have written. V means potential, but here I am writing the V as E. E means here is a EMF, which is one and the same. V and E are one and the same. So that is why E is equal to, I can write W by Q. So that is why potential developed is, E is equal to, EMF is equal to W by Q, which is equal to, W is equal to Q into B into V into L divided by Q. So Q cancels out, it cancels, so you left with the V. So this is the same expression we have got in the previous cases. In the two-way also, we can derive the expression for EMF induced. And whatever the force are written here, what is the equation for force? That is F is equal to Q into V cross V. This force can also be called the Lorentz force. We already know about the Lorentz force. It is a force acting on a charged particle in the presence of both electric field and a magnetic field. Here the charged particle is moving only in the presence of magnetic field. That is why Lorentz force is equal to the Q into V. Otherwise, Lorentz force F is equal to Q into E plus Q into V cross V. That would be the formula. But here we are writing only force due to the magnetic field, since there is only a magnetic field. And here Faraday giving an explanation how an EMF is generating by the movement of particle, by the movement of rod. So this is what he wanted to explain. And let us think in another way. For example, what if this rod is not moving and if there is an changing magnetic field? What will happen? That is what we want to see. Okay, if that is a condition where I told you that this rod is not moving in the presence of external magnetic field, but there is a changing magnetic field. In that case, what will be the Lorentz force acting on that conductor? How to write? We know the formula for Lorentz force. That is F is equal to, let me write here, which is not required for your examination, but you should know the things. You should have such a knowledge. So that is why I am telling you. So the Lorentz force acting upon that, Q is equal to, what you can write? Q into E plus Q into V cross V. What is V? V is a velocity. Here we told that the rod is not moving. We are keeping the rod as a stationary. Instead of moving that, we are changing the magnetic field, which should be to that coil. So that if the velocity is equal to 0, there is no velocity. Then what will happen? F is equal to Q into E. But whether electric field exists there? No. We have applied only magnetic field. Then what to do? Then what we have to assume that there is a change in magnetic field, there is a varying magnetic field that will produce an electric field. Because the force cannot be zero. Because we know that whenever the change in magnetic flux is linked with any conductor, the current will flow. If the current has to flow, then there should be a force. Then where does that force come from? That is because of the electric field. But we have not applied any electric field over there. Then where does it come from? Then we should assume that this electric field is generated by the varying magnetic field. So this is a significance of the Faraday's law. He is giving the relation between magnetic field and magnetism and the concept of electrostatics. I mean, he is giving the relation between electricity and magnetism. So this is where we can clearly see the relation of electromagnetic field, because here we have to say this electric field should be generated by the magnetic field. So this is a concept you should understand, and which will give the concrete hold of this concept.